Thank you very much. I would like to thank Professor Fritsch and organizers for giving me a chance to present my recent talk in this warm and exciting city of South Asia. Okay, this is title of my talk, and you will see what I mean by this title. I start by wondering whether the Higgs boson is a God particle. If you look at this cake of the universe, the Higgs boson does not look like the God particle. The Higgs mechanism produces only 2% of the energy of the ordinary matter in the universe. That means 0.1% of the total energy of the universe. Interestingly enough, which was also pointed out by Professor Fritsch, 98% of the energy of the ordinary matter is produced by nothing, from nothing. By from nothing, I mean that they would be produced even if the mass term in the standard model at the beginning vanishes. So we may ask ourselves what the origin of these portions is. As for dark energy, it could be the cosmological constant, but we do not know at the moment what it is. So in this talk, I assume that the dark matter and Higgs mass term are produced by a non-perturbative effect in a non-abelian gauge theory, like the proton mass in QCD. Let me consider the situation, what would happen if the proton mass were created from nothing. By from nothing, I mean that the current quark masses are set equal to 0 in QCD. There is no big change for the proton. It just loses its weight about 2%. However, if you put it at finite temperature, there is a big change. This famous Columbia plot was already shown in the first talk of this morning session by Professor Cabana. This plot shows that the nature of the chiral phase transition changes depending on the current quark masses. This is a physical point, and at the physical point, the chiral phase transition is crossover, as was already mentioned. But however, if the current quark masses vanish, the chiral phase transition becomes first order. Okay? This graph shows the chiral condensate against the temperature. It shows the transition is a first order. I have computed the chiral condensate using the Nambu-Yonagashima model, which is an effective theory for chiral symmetry breaking in QCD, in the massless QCD. In the massless QCD's projection, and as far as I know, there is no lattice computation for the massless QCD. So this critical temperature of 67 MeV is a prediction. Since it is a first order phase transition, it can produce gravitational wave background. The observable is basically the average energy of gravitational wave as a function of its frequency. This is defined here. And the calculation of the gravitational spectrum is, at least for me, partly outside of particle physics, so I cannot compute everything. Okay, as far as I understand, there are three mechanisms that produce gravitational wave by phase transition. Since the phase transition is the first order, there will be bubbles. And for the phase transition field theory, the bubble means the border of two faces of broken and unbroken faces. So inside of the bubble, the chiral symmetry is broken. On outside of the bubble, the chiral symmetry is unbroken. These bubbles collide with each other and thereby producing gravitational waves. Even after collision, the turbulence in the standard model particle plasma can occur and can also produce gravitational waves. Furthermore, it has been shown that if one deducts the assumption on the incompressibility of the standard model particle plasma, sound waves can occur and produce also gravitational waves. Fortunately, there are approximate formula for us which I can use to calculate the contribution to the gravitational spectrum from each mechanism. From the field theory side, I have to, for instance, compute the latent heat that is released at the first order phase transition. Also, duration time of the transition. The duration of the transition can be computed from the tunneling probability of the first vacuum to the true vacuum. The wall velocity here also enters into the gravitational wave spectrum, but I assume wall velocity is an independent parameter. So with these parameters, which I can compute and assume, you can compute the gravitational wave spectrum. And I did for the massless QCD. This is a gravitational spectrum for the massless QCD, where I assume that the wall velocity is the sound wave velocity. And you see that the peak frequency of this spectrum is few times 10 to the minus 5 hertz. This is a theoretical result for the academic theory, because all the quark masses are set equal to 0. For the real QCD, there is no such thing, because the chiral phase transition is not first order. Okay, I put this, or I compare this with the sensitivity of various experiments. This is shown here. Vargo, LIGO, Kagura, so U is missing here, I think. Ground experiments with sensitive frequency of 100 Hz. And LISA and DeCigo are space-based experiments. The sensitive frequency of LISA is in the mid-Hertz range, while that of the DeCigo is in the decihertz range. I borrowed this figure from Mrs. Kuroyanagi. I forgot to change the Japanese here. This stands for the pulsar timing. So this is a prediction from the massless QCD. And fortunately, this signal cannot be measured because experiments are not sensitive enough. However, note that the peak frequency of the gravitational spectrum that is produced by phase transition is proportional to the critical temperature. So we expect a critical temperature of TeV for the generation of Higgs mass term and also dark matter. That means this spectrum will be shifted to the right so that it could be measured in future experiments. Okay. For the rest of my talk, I will present two realistic models and calculate the gravitational spectrum. If we start with a theory containing a mass from the beginning, there is no chance to explain its origin. So this led us to the idea of scale invariant extension of the standard model, or conformal extension of the standard model. And here I assume that the Higgs mass term and also dark matter are entirely produced by a non-perturbative effect in a non-abelian gauge theory. So model 1 uses the chiral condensate, as I described in the matrix QCD. Chiral condensate in a non-abelian gauge theory, which is only weakly connected with the standard model. So it's a hidden QCD model. This is the Lagrangian for this model. This part is the hidden sector part, and this is the standard model Lagrangian, but no explicit Higgs mass term. The simplest mediator for the connection of both sides is the standard model singlet Lear scalar S. In the hidden sector, I have this Yukawa coupling that breaks chiral symmetry. And in the standard model sector, I have this Higgs portal coupling. Note that the hidden sector fermions are standard model singlet, okay, in contrast to the technical model. And also at the classical level, we have scale invariance and un times un chiral symmetry that is broken down to its diagonal part, vector-like diagonal part, by this Yukawa coupling. Therefore, the Nam-Goldstone bosons associated with the chiral symmetry breaking in the hidden sector, so the hidden mesons, are massive and also stable, in contrast to the real QCD. Therefore, the hidden vector-like fermions. No, it's hidden fermions. Okay, hidden fermions are singlet. So these hidden mesons can be dark matter, therefore. So we started using the effective theory, and in fact, it can be a good dark matter. So this graph shows the spin-independent cross-section of dark matter of the nucleon, and as a function of dark matter. Red points is a prediction for the case that the vector-like SU3 times U1 is intact. And the blue points is a prediction for the case that this SU3 is broken down to SU2 times U1. And this black line is a central value of the xenon one-ton upper bound. So you see that most of the predicted points are below the experimental bound. Now, phase transition. In this realistic model, there are three webs. The web of Higgs, this is related to the baryogenesis, electroweak baryogenesis. But in the simplest model, there is no CP phase. That has to be introduced to make baryogenesis possible. In the hidden sector, we have chiral phase transition. If the Yukawa coupling Y is small enough, we can expect the phase transition is first order. So this is the benchmark point analysis. There are basically five relevant independent parameters, one Yukawa coupling and three quartic couplings in the Higgs sector, and one scale parameter. We have to have a correct Higgs mass, correct Higgs web, and also correct Lyric abundance. Moreover, the mass of the singlet, this is here, is not a free parameter in this model, because to get a correct Lyric abundance of dark matter, we have to use a resonance effect in the S channel of dark matter annihilation. So this is not a free parameter. So effectively, 4 parameters has to be used to satisfy this constraint, giving only one free parameter. For instance, Yukawa coupling. For this choice of the Yukawa coupling, I have this phase transition. The left panel shows the electroweak phase transition. Vertical axis is the Higgs web over the temperature. You see that the temperature, the transition does not look first order. It looks like second order phase transition. The right-hand panel shows the web of singlet S and sigma. Sigma is mean field standing for the chiral bilinear. You see from these figures that the chiral phase transition in the Hindoo sector looks like, yes, this is a first order phase transition with a critical temperature of 607 GeV. Therefore, as I told you at the beginning, you can expect the gravitational spectrum of the frequency in the decihertz regime. So we have done this analysis, and we made again the benchmark analysis for these 4 benchmark points, and the predictions are these concave curves. And if you look at these curves, you see that they could be measured by this Japanese project this cycle. Okay. So this is a first model. Then I come to the second model. Second model uses the condensation of scalar bilinear instead of fermion bilinear in a non-abelian gauge theory. Scalar condensation, or condensation of scalar bilinear, was discussed and also phenomenologically applied in the past by these people. But here we use it to generate Higgs mass term in the standard model and also dark matter. So this is Lagrangian for in the hidden sector. Again, we used effective theory in the mean field approximation, and this is the example of the effective potential for this parameter. Effective potential as a function of F. F is a mean field in the mean field approximation, which stands for the scalar bilinear. So you see that the scale symmetry is in fact spontaneously broken by this condensation. We studied also the phase transition at finite temperature. The right panel shows square root of the web of F over temperature against the temperature, and the left panel shows the potential at and near the critical temperature. You see from these figures that phase transition, scale phase transition, is in fact first order. Okay. We did this study. Well, we are motivated to study this, symmetry breaking of spontaneous symmetry breaking of scale symmetry by this paper, in which not a hidden sector QCD is used, but the real QCD is used to make bilinear scalar condensation possible to produce Higgs mass term in the standard model. Here, we use a hidden sector model. So this is again the hidden sector Lagrangian, and this is again the standard model without Higgs mass term. And in this case, in contrast to the first model, it's not necessary to introduce a mediator because this Higgs-Potter coupling is possible. Now, in the effective theory, in the mean field approximation, one can compute various things analytically. For instance, I can compute the Higgs mass, which is given here. As you see from this formula, that the condensation of scalar bilinear is in fact the origin of the Higgs mass. In the mean field approximation, you can also compute or introduce the excitation of the mean field vacuum. So sigma and phi are excitation of the mean field vacuum. Once again, because we assume that the condensation does not break flavor symmetry, phi is stable and can be a dark matter. So we did this analysis. So again, the horizontal X is the spin-independent cross-section of dark matter of nucleon, and here is the dark matter mass. This is the parameter, as you see here. We assume that the number of the flavor is 2 and the number of the color is 6. So the maximal flavor group is U2. The red point is the prediction for the unbroken U2. But you can break U2 by scalar couplings. I assume in the U2 case that the scalar couplings, there are 4 scalar couplings, respect the U2, but you can break U2 explicitly by scalar couplings. For instance, in U1 times U1 or U1 times U1 times Z, then you get this blue rosa points. You see this model is consistent with experimental bounds. Again, phase transition for this parameter. On the left panel, you see the electroweak phase transition, which looks like the electroweak phase transition in the first model, and it looks like second order. But in the hidden sector, you have scale phase transition. This is a first order phase transition with a temperature of 323 GeV. Therefore, we again expect the gravitational spectrum in the decihertz regime. So we did this analysis. This gamma is an additional parameter we have to introduce in the mean field approximation. Yes. So depending on the gamma, we have different prediction, but again, the peak frequency is in the decihertz regime, and this could be measured by this cycle. Okay. Now I come to my conclusion. My talk is very fast. Okay. So my conclusion is this: the dark matter mechanism may be tested at future gravitational wave experiments. Okay, thank you very much.
Any questions from the floor?
Yeah.
My question is, in these first order phase transitions, do you employ the thin wall approximation or?
Partly yes and partly not. We compared both. We compared both, yes. We always check whether the thin wall approximation is correct or not.
Does it make a significant difference?
It depends on the parameter. Okay. Sometimes it's very good, and sometimes it's not very good. But in the QCD case, the thin wall is not that bad. Yes.
So my question is from the very beginning. Yes. You said that the color phase transition would occur at without Higgses or whatever you can replace Higgses with at something like 100 MeV or not.
No, I am not going to replace the Higgs.
I'm not saying that you are going, but it's true that the color phase transition occurs.
Yes.
And for the proton, it's unimportant whether you have these Higgses or not,
yes, yes.
Except it can be very important through the whole understanding when the color phase transition occurs. So I would guess it's 1 TeV because this is just proton mass, and the nature went through this, universe went through this procedure, and at that time all the hadrons, proton and neutron included, were born or made. So where do you guess your phase transition? How would you expect that the color phase transition would occur if no Higgs would be present, so without masses of quarks and leptons included.
In the real QCD, the chiral phase transition is a crossover phase transition of the temperature is about 160 MeV. This is the real case. The Lattice people can compute this chiral phase transition temperature. Yes, I am computing the phase transition temperature without quark masses. So it seems that the temperature depends on the quark masses.
Another question?
That's true.
Yes.
I will talk tomorrow. That's the QCD phase transition may be
Yeah.
completely different in the scale invariant models as well, a certain class of scale invariant. But
Yeah.
just answering the Paul's question also, it really depends. The width of the potential dynamics of the phase transition really depends what type of peak frequency you are picking up there, because in those formulas which you showed the references. The nucleation happens almost instantaneously. That's the approximation is taken. But if the nucleation takes a substantial amount of time, bubbles grow bigger, and roughly the break frequency is the inverse size of the bubble, and so the frequency can go lower, much lower.
Yeah.
So it's,
But don't ask me about the error. I don't know.